Now take a look at this. And just look at the center of the screen. You can blink. Try not to move your eyes too much. And keep your eyes in the middle where that dot is. So we're going to sit here for a little bit. Did you see an American flag? If you did, you just experienced opponent process theory. And this tells us that there's more to color than trichromatic theory. Why? Trichromatic theory says absolutely nothing about staring at green and afterwards, after that green is removed, seeing this illusion, this after image of red, or staring at black and seeing white stripes afterwards. Staring at yellow and perceiving blue after it's removed. So you should have probably seen this traditional red, white, and blue American flag after staring at this yellow, green, and black one. And this is going to be relatively systematic for us, the way that these colors kind of work. So if you have, let me pick a good color here. There we go. If you have black, the after image you see will be white. If you see green, the after image will be red. And if you see yellow, the after image will be blue. Let me repeat that here because it didn't show up too well. And this is actually a two-way street. We can stare at red, the after image would be green. We can stare at white, the after image would be black. We can stare at blue, the after image would be yellow. So this is telling us that something different is happening in our visual system, that there are neurons that get stimulated. In other words, they fire more when you view one color but have an opposite response when they see another color. And this leads to these opposite colors. So if you look at a color wheel, the colors that create the after images are going to be these opponent colors. And these are the three pairs. So there's red and green, blue and yellow, and then black and white, although that's really achromatic because there's no color there, right? So when we talk about color, it's the red-green channel and a yellow-blue or blue-yellow channel. So let's combine what we know then about color vision. If I'm looking at that red geranium, the red from the petals comes about because the petals are reflecting these long wavelengths of light. These long wavelengths of light activate a particular type of cone that specifically absorbs long wavelengths of light. The red geranium will not reflect the short wavelengths or the medium wavelengths. So if we look here at our cones, we have the 3 cones, red, green, and blue. So the red from the geranium petals is going to stimulate this long wavelength cone here, but not the medium wavelength cone or the short wavelength cone shown here. And so that long wavelength cone is going to absorb that light, that long wavelength light from the red flower petal, and it's going to go here to this ganglion cell. And the ganglion cell is going to react by being excited by the long wavelength cone. And so it's a ganglion cell that is excited by red, but it's inhibited by green. Likewise, there is a ganglion cell for the blue and yellow. And it's excited by yellow, and inhibited by blue in this example. Now, reality is that you can have a ganglion cell that's inhibited by red or excited by green. It's arbitrary. In other words, which one gets excited, which one gets inhibited. The ganglion cells are always going to be red or green, blue or yellow. You're not going to mix them. There's not any ganglion cell that processes green and yellow, for example, or blue and red. No, it's always red, green, or blue, yellow. So here we have the red, green ganglion cell. And on the other side, we have the blue, yellow. That sets us up to better understand color blindness. So in color blindness, a person is missing one type of cone. It could be the red, green, or the blue. In other words, they're missing the long, medium, or short wavelength cone. They only have 2 functioning types of cones. Don't worry about these terms. You won't be quizzed on them, but do know that there are terms that describe each type of color blindness. Now let's take a look at this flag here on the top and then the one on the bottom. So I'm just thinking of them as colored stripes, or the stripes on a flag. In normal vision, this top stripe appears red, and this 4th stripe down appears green. And here are these colors as seen by a person who has protanopia. In other words, they are missing the long wavelength cone. Notice they don't really see this top color as red, so if you have normal color vision, this might appear as kind of a greenish brown hue. And you can distinguish between that and this top red color. So a person that has red-green color blindness, they are not seeing the red because they're missing that long wavelength cone. But notice they're also not seeing green. Why is that? Why would lacking a long wavelength cone, which is critical for seeing red, also prevent you from seeing green? Has to do here with the ganglion cell. Without the cone working, this ganglion cell can't work, and so we knock out both red and green in that situation. So that's true whether you're missing the long wavelength cone or the medium wavelength cone. You're going to miss seeing both those colors in the same way that a person who has normal color vision would be able to see them.